then the afternoon is free, so you'll be able to work. And it's my pleasure to introduce Florian Pop, all the way from Pennsylvania, who will tell us about the Pro-L abelian-by-central I/OM, which means Ihara Oda Matsumoto.
So I want to thank all those who succeeded to make it here this very early morning. And so I repeat the title of my talk here. Abelian-by-central.
Now, I should say from the beginning, IOM stays Ihara's question and Oda Matsumoto's conjecture, and I will explain in maybe down in the 10th line of my talk what this question is about. But so first I want to speak about the initial motivation for this. And the initial motivation is something which maybe could be interesting for everybody, even for second year, well, first year grad student, which means give a non-tautological description of the absolute Galois group of Q. Now, in many talks, this was an algebraic group, but with other properties. So here is this. This is one of the most fundamental objects in number theory and arithmetic geometry and so on. And you'd like to understand this guy, and we know what it is, namely the automorphism of Q bar. The question is there another description which has nothing to do with solving equations and maybe also not with rational numbers? And there were, so one attempt and one proposal comes from, I will say here, by understanding or by using the action of GQ on geometric fundamental groups or algebraic fundamental groups. And this also shows that this talk is about this conference, about this program, sorry. No, all the talks were about this conference, but this is intimately related to the subtopics of the NEG program. Okay, and I will make you a very easy and fast introduction to what I mean. So let's X over now, okay, so let K be some base field. Many of these things can be done very generally. And then X over K be some geometrically integral variety, maybe normal, well, smooth, and with other nice properties. Then we denote by X bar the base change to algebraic closure. And in particular, this is an integral variety. And you have, and I denote also then pi bar of X is by definition the pi 1 of X bar. Well, with some geometric point which I will neglect because I view this, I'm sorry, Min Hyung, in the category of groups, but without morphisms as homomorphisms. Therefore, the base change, the base points are irrelevant because they differ without forms. Okay, and then we know that you have an exact sequence of the following form: pi bar of x, pi 1 of x, and here is the absolute Galois group of k. And in particular, you get a representation rho x defined on the absolute Galois group with values in out pi bar of x, which means all the outer isomorphisms of this. And it's clear how do you work. So you simply take any sigma from here, take a representative that acts on this group by conjugation, and that gives you this. And if you take another representative that differs from the initial one by some element from here, that means by an inner automorphism. And we speak only up to outer automorphisms, everything is fine. And now this is functorial in the following way. So functorial in the following way. Let's take some morphism of varieties as x and y as there. And then you get this morphism gives rise to pi 1 bar of x goes to pi 1 of f into pi 1 bar of y. And if you plug in here rho x of some sigma and sigma in gk, then you have here pi 1 bar of x, pi 1 of f, pi 1 bar of y, and if you put here rho y of sigma, then this is commutative for all possible sigma. And what is the conclusion? So from this, it follows that this system is an element in the automorphism group of pi bar. So we should think of pi bar as an, maybe here, you should think of pi bar as something going from varieties over k into groups. And if you work with base points, there are several difficulties. Well, there are no difficulties, but then you have to define everything in a corresponding way, and it will be not groups, or maybe groupoids and things like this. And then you still get a functor, but in this way you get straight away a functor and general nonsense. So for every functor you have an automorphism group of that functor, and what I explained here means simply if you just translate it into general nonsense follows. You have this. Okay, what does it mean?
To be consistent, you should write out.
Let's take it. So this is the automorphism group functor of this. So this is really the automorphism group of this functor.
I bar already encodes the outer automorphism.
Oh, okay.
Yeah, okay. But you're right. I could, one could, depending on. Okay, and what is the conclusion? So therefore get some.
Comes from the annotation. Once it's called pi bar and one it's called pi lower 1 bar.
That is only mistake. It's something missing. Okay, so maybe that was also a reason for confusion. So hence get. So if you have any maybe V category of k varieties. Pardon?
No, the functor is there. I
Okay.
didn't say what it is.
I like it. So everybody is
We
going.
all understand.
So if you have a category of k varieties as above, so as above, then you get pi bar, and now I define it like this, yeah. So defined on with values in groups, where this guy should be pi 1 by restricted to v, yeah. And in particular, you get IV, which doesn't mean that it's an inclusion on GK with values in automorphic group of pi bar V. Okay. Now I'm in the position to tell you what Oda and what Ihara and Oda Matsumoto did. So then here is IOM, which stays for Ihara's question. This was maybe in the 1980s. I do not know precisely when. And Oda Matsumoto conjecture, and I can tell precisely when I heard this, it was in 1996 in Oberwolfach. Okay? And they say simply that a recipe which will give you a non-tautological description of GQ is the following. So this is I varieties over Q defined on GQ in automorphisms of this P bar varieties over Q should be an isomorphism. Okay. Now maybe 2 words about why is this why is this philosophically interesting? Because here stays something which has nothing to do with numbers. Imagine so for such varieties, well, for nice varieties, so what is pi 1 maybe? Okay, you can write here. So if you have such an x over q, then pi 1 of x is nothing but the completion of pi 1 top of x of c. Now this is something which has to do with combinatorics and other things like this, but nothing with numbers. You complete, you don't have to do, pardon?
X bar. X bar.
Thank you, yeah. So, and also, Ellen, I thought I succeed to hide it from you through this, but it doesn't work.
But I can't see either.
Okay, so maybe here, pi 1 bar of x in this situation here is actually pi 1 top of x of c, which is a topological space completely profinite, and then this has nothing to do with numbers or things like this. And well, there is something which has to do with numbers, namely that these are subject to some restrictions coming from the morphisms between varieties, and therefore, so this is only half satisfactory. But actually, from what I'm going to tell you later, you will see that actually it really has nothing to do with numbers. Okay, so, and as I said, at least philosophically, this is interesting because this gives you really a new recipe to compute the absolute Galois group of Q in a completely, the recipes of a completely different nature. Okay. Now, okay, so maybe before moving to the next part of the talk, I will speak about some variants of this.
Oh,
No.
Just trivial objection, but if you look at pi bar, of course, that for a fixed variety that has nothing to do with numbers, but you're looking at it as a functor and category of varieties over Q.
Yes,
so
so this is why I say. So, thank you, Mignon. I'm going to solve this. I'm going to solve this problem in the course of the talk. And exactly so, the point is, actually, myself, I gave talks, I gave thoughts to this sometime, so for some time every year after 1996. And the more you think about the problem, the more you understand things like Mignon points out that, it's not exactly what you think. And maybe this is really only philosophically of importance, because this guy on the right you have no chance to understand it a little bit better or to describe it. And therefore, it's worthwhile to think about variants of this where the things would become a little bit maybe stronger conjectures, but which would give you the impression, at least, that you really give a new description of the absolute Galois group of Q. And our variance of this is, so maybe A replace Q by other fields, e.g. number fields. Okay. B replace var Q by smaller, or maybe by simpler categories, maybe V.
So at this point, could you make precise exactly what category of varieties you're looking at?
So for this question, as the author put it, were only smooth varieties, but they allowed also something which is called, they would allow morphisms, which I would call them connecting morphisms, which are not necessarily, which are kind of rational maps. So it was, but for instance, the conjecture was in Oberwolf, conjecture was made for smooth varieties and dominant morphisms.
But why not? Why automorphism? Why not take Taiwan with base points?
I said this before, because that complicates the things in some precise way. You can formulate the conjecture also in that way, but it would be much more technical. Yeah. But so, I mean, the experts know what to do in order to replace this, the automorphism well, to work with base points, okay? And now C, why not? So replace phi bar by other fundamental groups. And finally, D may be combinations of the above. Okay, maybe I should say some words to this. Well, here there is nothing to say, but what means replace, well, to B? Replace, well, for instance, here there was some, when the story started, so then Grothendieck suggested that you should do the following, yeah? V should be, so V, or study there, yeah. Let V be the Teichmüller modular tower, which is T. What is this? Well, it's the category of all the MGNs and plus, so GN, plus connecting homomorphisms, whatever that means. And of special interest here is maybe V0. This is my notation, yes. MZ4, M05. Now you know that these are, this is P1 minus 3 points, this is P1 minus 3 points minus the diagonal. And the connecting homomorphism I will not explain, so, yeah. Well, and then this sits inside V1, which is MZ4, M05, M11, which we've seen also in Hiraki's talk. And these are called the first two levels. And here there is a lot of work, so a lot of work by many. And these many include people like Ihara, Drinfeld, Delin, Loschak, Schneps, David Harbeit, Nakamura, Matsumoto, and. But I mentioned from all this something, just that you can relate it to what I'm doing, to something which is not obvious, is not instantly is not trivial, yes? So and the first one is, what is out pi bar of V0? Well, it turns out that this is the famous Rodin-Teichmüller group. Which in this situation was introduced by Drinfeld and so on, but then soon after then he realized that the things are interesting if you work in the algebraic context. Okay, and maybe here is a really impressive result by Nakamura-Schneps. What they proved that actually out pi bar V1 equals actually out the whole Teichmüller modular tower. And the point is, and this is R, and in both cases here, these groups can be described in a concrete way. The groups can be described as subgroups. Can we say concretely, yeah? As subgroups of out p bar of p1 minus 3 points. Now, what is this guy? p1 minus 3 points is the p1 minus 3 points. The geometric fundamental group is generated by the 3 canonical loops. And then you have a free group on 3 generators with relation product equals 1. That is a free group with 2 generators. And every automorphism is then precisely given in pro words, which tell you where the 2 generators x and y go. And now what these guys did is really they explain precisely what conditions must satisfy these automorphisms which describe this group and this group. So note that actually in all these cases, these are subgroups of that group. Okay. So, and I am sorry here, very, very sorry. So very, very, very sorry for all the many names which I do not mention here, because that would be a completely different talk. Okay. Now that was B. Now to C. So replace pi by other fundamental group. So the most canonical way to do it. So one possibility is replace pi bar by, well, for instance, by every so-called what the group theory is called a verbal quotient. What is a verbal quotient? Well, with something which you can write down, and that what you can write down will be invariant under universally. That will be invariant under taking quotients. That means replace this by maybe pi bar L, which is the maximal pro L quotient. But why not? So this is maybe 1. Another possibility is replace this by, and now I hope my handwriting is clear enough. So this is pi 1c, which is maximal pro L abelian-by-central quotient. What is it? So in this group, you take the L infinity central series, and this is simply the quotient by the second central subgroup. And you see that actually this has a canonical map onto pi 1, which is by definition the maximal abelian, pro L abelian quotient. And this projection is encoded actually in this because it's simply the quotient by the commutator. Okay, maybe then why not? So replace this by the pro unipotent completion. Which I learned a lot about during this conference, and I also realized that this would be really a very interesting story. And then why not? For well, something which should have integral aspects to it. Yeah, so replace this by quotients reflecting an integral structure. And I will not say anything more about this. Yeah, but well, maybe at the end I will mention more. Fine. Now, what I'm coming now to my second point of the talk, which is today. Now, today I will speak about, so K is a number field. Then for variety, I take any variety x, maybe over K geometrically normal, integral. Although, so integral normal doesn't have to be. Okay, for this I define Vx to be the following category. All the u in x, Zariski open, so not all. Zariski open. Basis of Zariski opens. So basis of Zariski open neighborhoods of the generic point, and the morphisms are inclusions, yeah? So only inclusions. Now you see, that this comes somehow towards what you, so this are really, so what does it, so the only morphisms in my category are like this. So for U contained in V, then simply identity. So you have here, so this has only the identity, and this is, okay, so hom between U and V is id U if U equals V is U V if U is contained in V. But this is all, and otherwise there are no morphisms. Okay. Okay. And then now I have to
So was this for the first year graduate students?
Pardon?
Was this for the first year graduate students?
Less. I think that less. These are for those who are by fourth first year graduate students. Okay. And now I do the following. By the way, so then what is out? No, out is in German, so out Vx. Well, you see that these are exactly all the f defined on x with values in x. Isomorphism, so such that, no. So this consists of this, what do I want to say? Now I have to be careful.
You have to respect all opens.
Exactly, so only this, yeah. So this is, so out of this is such that f of u equals u for all u.
Lies in U. Lies in U.
Pardon?
F of U lies in U.
Contained.
So there you're, okay, so this.
No.
F of U, I would say lies in U. Maybe
Well, but if it is automorphisms,
automorphism.
yeah, then, okay.
That's clear? You cannot
So
pass-
actually, this, but where in all the in the category of I allow here.
Everything's the inverse.
Okay. Sorry. Okay. So I define this. Yeah. So to calm down all the discussions. Yeah. Okay. Now, what is then the
Is it clear that this is for all u's because you only took a basis?
So for all u in, so it was right what I said. Okay, and that is actually essential later on, yes. Okay, and now let's look a little bit at what happens with automorphisms. So what is now what of p bar v x? So this is the set of all sigma u with sigma u in what p bar u, which satisfy my compatibility conditions such that for all u in v in u, better lexicographic, in as, so you have pi 1 of u v, so this subjects onto pi 1 of u canonically. Okay. Yes, and now here is a sigma u, sigma v. So this is the canonical pi 1 of bar of v, so of u. So that all these are commutative, yes. And now what happens with this? So let's go with this to ought. I did not finish this today. Actually, yes, sorry. I'm explaining what I'm doing. Yes, and now this is what I do on the group theoretical side. So I take now ought of bi-central u vx. Yeah, and what happens when I restrict such an object here? So when I say, well, I get something, I should call them this sigma, yes. Then I get some sigma central u for all u, and actually that is here. Why? Because this quotient of every fundamental group is somehow verbal, and okay, nothing to say. And then you have further on a map onto. I put a c here, pi x. So what are these? These are the pro-L, maximal pro-L commutative abelian group quotients. And then because, again, everything is verbal, so every automorphism from here defines an automorphism here. And here I denote the corresponding automorphism simply sigma u. Okay?
So pi down is a pi abelian?
This is pi abelian. It was there, pro-maximal, yes, in 2. Now note that actually this is contained, yes? So this guy is contained and usually not equal. Well, no, usually in ought pi abelian, yes?
What is this ought C? So these are automorphisms which live?
Which live in the image. Or which, yes, which left. Okay. So this is the preparation. I just wanted to explain it very slowly. And now the theorem is the following. So it's, I hope that it's clear for everybody what I'm doing, yes? So
can you just recode what the Vx is?
So I said Vx is the set, it's a basis. You take some basis of Zariski opens of the generic point.
Okay.
If you want, actually it's okay. You just take any closed subset of codimension, at least, well, every proper closed subset, and it's enough to take open all the open neighborhoods of that, and everything works, but I don't want to make it too technical. Okay, but anyhow, so you take categories, you fix a geometric integral normal variety, and you take simply opens, so basis of open, Zariski open subsets, and then for that you have this picture. Yes. Okay, and now maybe a definition before I move on. So let's call that u in x is called pi 1 maximal if for all U dashed such that U is contained in U dashed, well, in X, everything is in X, yes, and pi 1 of U maps isomorphically onto pi 1 of U dashed, then U should be equal to U dashed, yeah? So the maximal means that actually Y, so you will see later, when you look at automorphism of this variety, you could rigidify the variety in an artificial way by simply taking away a point only, which is not seen by the fundamental group theory. And then you do not have a nice, the result I'm going to tell you now. And now, I do not know, maybe I can now, can I erase this here? Not this here, but what? This. Okay. Now the theorem I want to mention here is the following.
If I want your, yeah, that's the same.
Yeah. Okay, now the theorem which I want to announce is the following theorem. This I call Pro L abelian-by-central Oda Matsumoto. Yeah, so I say now let X be geometrically integral such that automorphisms of X bar over Q bar is the same as automorphisms over Q bar of its function field. Yes. For instance, P1 has this property, but anyhow. If X is of general type, then usually you take the function field. It has only finitely many birational isomorphisms, and how should I know? There are only, this has only finitely many automorphisms, and then you can blow up X and so on, and all these are defined on X and so on. So this is actually no restriction in general, yeah. And then let nu X now be category as above, such that all U in nu X are pi 1 maximal. Once again, otherwise you can rigidify this category in an artificial way, which is not seen by the fundamental group theory. Then one has an exact sequence of the form sorry. And here are the central ones, yes. Okay. And I will say maybe in particular, if X is geometrically rigid, it is the automorphism groups over Q bar of X bar only identity. Then you see that this is trivial, and GQ is exactly the automorphism group of those, well, of this very small, of the fundamental group of this very small category. Well, you will say, but this is complicated. The point is, you detect the automorphisms here, which definitely are detected by this because it's just the image of this automorphisms, yes. Yeah.
You really take all automorphisms of Q1, not just some function here?
No, this is all, yeah. So actually, sorry, maybe I should have said where, here. So, yes, thank you. Maybe as a remark, thank you, that is a good point to make. Actually, the injectivity of this comes usually for almost very easily. Yeah, so vacuum. So remark by the so-called Bailey's trick. Usually, so IK, I var Q is injective, but actually it is injective on all categories which contain, for instance, P1 minus 3 points, or which contains, and usually injective for almost, I would say almost all V. Yeah, so that is not the problem. The problem is really the subjectivity. Okay, so I want to finish now. Yeah, then this equals GQ. And maybe I will say a corollary. Well, it's not a corollary because you really have to do a kind of work of another kind.
With a C? With a C?
C. Automatic C.
Superscript C.
Yes, thank you. This is very essential. Yes. So remark, actually here, the same is true without pi. So from this it follows, from the theorem, one gets also, which is a much weaker result, yes. You will say, maybe not, but if you talk to these guys who do profinite group theory, they will instantly tell you, oh yeah, it's clear. Hence the classical Odamatsu EO. Okay. So that's it. And now I have 15 minutes left. Try me show you something about the proof.
So this remark, you're saying that you get this for a single Vx. So
Yes.
That's the general thing.
Well, the point is, if you have it in the category of all the varieties, among other things, these are subcategories, yeah? And if all of these are rigid, then there is no chance to have.
Is it easy to produce such a pi1 maximal?
Yeah, so the point is, for every pi, every u. So first, every u, you can see by Zorn's lemma, or maybe Noether induction, you see instantly every u is contained in a pi1 maximal. And after that, what you simply do is, you have a pi1 maximal, you erase one divisor, take the pi1, you have a pi1 maximal, erase one divisor, take the corresponding pi1 maximal. Now erase two divisors, then go on and you see that actually everything is.
So I'm a little bit confused by your odd Vx. Isn't it very often trivial, in fact?
Yes, this is very often. Very good. Now, let's suppose that actually you take all the pi1 maximal opens. Then odd is trivial. Maybe also that. Thank you. So, actually, I did not. I still had something in the back of my mind too. If Vx equals the all u in x, you open pi1 maximal, then this odd is trivial. Yeah, so then odd of pi of Vx is 1.
But even with it, I mean, with any basis, I find it hard to think of a non-trivial instance.
With every basis, not only with Q. This is very general, yeah. So the point is, so think of a variety and take the automorphic group of the variety, and now you want to rigidify this.
Right.
Well, if maybe it's not completely obvious, but there are ample divisors on the variety such that they are moved, so that the automorphic group acts, transitively on the orbit.
Right.
Not transitively, that's always on orbit, faithfully on the orbit. And now what you do, you erase only one divisor from the orbit. In this way, you kill at least one automorphism and so on. And when you erase more and more and more, you see that actually nothing is left in your automorphic group.
I know, but my question was, I find it hard to imagine a situation where this is non-trivial.
Ah, yes, so there are non-trivial things. Yeah.
There
For instance,
there must be an assumption on the dimension of the variety, right?
did I know? Thank you. This is essential. Sorry.
Because it's false for
I-
a point.
Yeah, point I was
Yes,
saying
yeah,
about
for
the
curves,
same
for
thing.
force, and so on.
I think
Maybe it's true for dimension too, but I can't prove it for I can prove it for special varieties. But okay, now maybe
Is your exact sequence split by the dimensional map? So GQ in what?
yes, that is exactly the canonical. If you choose Q bar as a base point, then that gives you a splitting. Yeah. Fine. Now maybe to the proofs. And I'm sorry that my friend Ida Bogomolov is not here. Actually, the main ingredient is what I call Bogomolov's program. And what is this program? Because we are in this country, is this. Yes, so what is this? So this was maybe around 1990. Well, actually, this is maybe less or equal to, yes? Earlier than maybe 1991. I learned from something. We announced this May at in Kyoto at the International Congress of some satellite conference to the International Congress. And what does it say? So now K is arbitrary, algebraically closed field, characteristic different from some fixed prime number L. And then you can see the K over K function fields. Now for the young generation, a function field is the function field of a scheme of finite, integral scheme of finite type over K. And for such function fields, you look at PCK as defined above. It's clear what it should be. PK. And then Bogomolov's claim was the following. Okay, now maybe I can leave it like this and you read it as you want. Bogomolov's conjecture, Bogomolov's claim. So if transcendence degree of large K over little k is at least 2, then one can recover. Well, recover has to be explained, yeah? So recover the function field from PCK. Now what means recover? So that means you can give a group theoretical recipe. Somebody gives you only this group. And then you should give a group theoretical recipe in such a way that at the end of the recipe you have this field, function field. That is, and if you are lucky, then you will even be able to recover the structural sheaf of models of this. You will be able to write down varieties, normal varieties whose function field is K, and the structural sheaf of those varieties, and so on and so forth. Yeah. And now, what is the status of the art with this?
Are you given small k, or is that also part of it?
No, you give only this. This is the only information you give. Somebody gives you, actually, even worse. Yeah? Somebody gives you a profinite or pro-L group, which is nilpotent of level 2. And then he asks you, tell me whether this is of this form, and if it is of this form, tell me what is K. Okay, now what is the status of the art with this? So theorem, and this is something which I unfortunately did not completely finish writing up here, but maybe I should give you first the status of the art as it was before. So status of the art. So this is K algebraic closure of a finite field is okay. But it's okay in a much stronger form, which I'm going to tell you in a second. So, and this was for transcendence degree equals to is Bogomolov-Schinkel. And around, maybe I don't want to say around the same time, but maybe. So in general, is by myself. And now the point is it's also okay K algebraic closure of a global field. Then it is okay if, now you see where from my transcendence degree is bigger than 2. And actually what I did here is K algebraic closure of some finitely generated field, then okay if, now a finitely generated field has a so-called crude, well, every field has Kronecker dimension, which of finitely generated fields is the transcendence degree, if the characteristic is positive, that means it's the dimension of every variety with that function field, and as function field, and over number fields, then it's transcendence degree plus 1, because the function field, the global number fields have dimension 1. So if the transcendence degree of K over little k, now transcendence degree, as I should say, is bigger than the transcendence degree of K, which means the not good. The dimension, yes, dimension of little k plus 1. And now you see, when this is the algebraic closure of finite field has dimension 0, the hypothesis is transcendence degree should be bigger than 1. When it's a global field has dimension 1, transcendence should be bigger than 3, than 2, and so on. And now for that, the theorem is, so, but there are many people who contributed to this idea. So let K be algebraic closure of a finitely generated field, and let K over K be a function field with transcendence degree of K over little k bigger than dimension of little k plus 1. Yeah. 1. And there exists a group theoretical recipe which recovers K over little k from P central K. And what are the properties of the group? This is functorial in the following way. More precisely, so the recipe is functorial in the following way. Given L over lambda, sorry, I have to put lambda because L is already used, so function field with lambda algebraically closed, and phi an isomorphism of, so now I say phi in odd, maybe I should say, okay, that can't be isom, okay. isomcentral of PKPL. Now, intuitively should be here. So what are these? You have these have maybe lots and lots of isomorphisms, but some are liftable to the pk, and these are these. Yes. Then, given such an isomorphism, there exists a unit, an L-adic unit, and there exists phi, an isomorphism of function fields, but I have to put here inseparable. Isomorphism of function fields such that this guy, now you give such an isomorphism between these. Now, naturally, so these are abelian groups. You have an isomorphism. You multiply it by an L-adic unit, you get further on an isomorphism. Now, the point is that you really can introduce such disturbances. If you give an isomorphism of this coming from geometry, you can multiply it by any L-adic unit, and a miracle happens. This is liftable to the central, to an isomorphism. If the initial isomorphism is liftable to is here, then also the multiplication of that with epsilon is there. So, but after you renormalize, then such that epsilon phi is defined by this. I is the pure inseparable closure because you must allow such things. And then, moreover, epsilon is unique up to p to z, p equals characteristic, and phi is unique up to Frobenius twists. Okay, now maybe let's, I want to show you very quickly the proof. How from this it follows the assertion of the theorem. Oh. Now look what you do. It's still there. Yes. Now take sigma.
Epsilon is unique up to what?
Up to multiplication by p to the z, where p is the characteristic. Now p is different from L, therefore p to the z is a subgroup in here. And you can't choose. So what means multiplying epsilon by some power of p means applying an Frobenius, where p is the characteristic. Okay. So now I'm glad that everything is still there. So what do you take? Let maybe take sigma u bar in R out of ux. Sorry, oh, in I1 Vx. Then you see that actually this means because this is a compatible system automorphism, this will give you a sigma bar in k of x bar. This is in ought C pk, where k equals this. Yeah. And now what tells us the theorem? The theorem says it follows there exists while you I need this I forgot to say, sorry. Where's the theorem? Here I have naturally to put, sorry. Yeah, or this acts this guy. Yeah, sorry. Okay. That acts this guy. Then there exists, well, up to renormalization with some epsilon in ZL times, follows there exists a phi star defined in on ki with values in so now there is no I because I'm characteristic 0, yes? K defining sigma k. And now, if you go through everything, then it turns out that for every u, there exists, so for every u, phi gives, what did I say? Now, because of this and because of the hypothesis, it follows that phi star is the generic fiber of some phi automorphism. Yeah? Well, actually bar. Okay, and after you have this, and now the claim is, I'm not going phi of u bar equals u bar for all u bar in u x. And here, proof, use the maximality. Use pi 1 maximal. Okay, and then, if so, it follows then that you get that phi belongs to out mu x, and this finishes the proof here. Maybe my time is up, but I can take 30 seconds only. That was my 4-point. Actually, why did I come back to this again? Because of the discussion here, and especially with Min-Young Kim and Mohamed Saidi. The point is that actually it looks like it would be very, very interesting to do this for analyze. So A, the pro-unipotent variant. And it looks to me that actually we are somehow too bound to the absolute Galois group of Q and of number fields, but concerning the talk by Laurent yesterday, and maybe also the number fields has to bound something. Actually, the automorphic part, they don't have any fears. On the Galois side, they have lots of fears, and everything must come from Galois representation. I think that this is maybe wrong. What you should really do is define interesting categories, find interesting categories of varieties, which you can call them, for instance, fields. The F1, the varieties of F1 should be such an interesting category, but also other things like that. And then take the automorphism group functor of some special kind of profinite group, for instance, the pro-unipotent variant, and that should be your Galois group. And now you look at representation of that, and then maybe the automorphic side really corresponds to something on the right side. Because this guy can be many things. So if you do this, then a GQ at once can sit inside a group. And the point is you should not look at all the representations, or even all representations should look good. You should look only at those which come from the bottom. Yes. In the same way, if you have quotients, then look only at the representations which are induced from the quotients and so on. So that is one thing. And the second point is, this was David Byrne's comment to my talk, which I gave at the Imperial, and then he said, what is the right variant, integral variant of this? So, what is the right integral variant of this? Okay, so I will stop here. Thank you.
We have time for a few questions.
Could you say pluripotent variant? It seems that if you take pluripotent part or quotient of Galois group, you will get very small representation.
Yeah, but the point is that still can see everything. But take here.
No, it's.
So this is not the. This is the pro-unipotent. The pro-unipotent. So as I said, it's exactly what I'm meaning. Namely, if you have, my conviction is that the automorphism group functor of the unipotent, pro-unipotent convention will be big. Bigger than the the absolute Galois group. And this is interesting to see what really it is. Maybe the Galois group sits inside, it's a sub, I'm convinced that the Galois group is, the absolute Galois group is a sub-quotient of that, even in this setting. Now, there are serious problems with your pro-unipotent. For instance, it's not clear if you just have an infinitely generated pro-L group, then I think Delin convinced me that there is no good pro-unipotent condition. But in geometric situation you have, because you have a canonical filtration. Actually, exactly this is why there are no good theories, because there is no canonical filtration in general. But in geometry, an object coming from geometry, you have the absolute Galois group is a profinite group in a canonical way. Well, it's a profinite limit of finitely generated groups, profinite groups in a canonical way.
Maybe I'll just make a quick comment. It's in a different direction, but this idea of generalizing Galois theory with appropriate categories, in some sense, this is the program of Mochizuki.
Mm-hmm. Well, as I said, I don't, by no means do I pretend it. I just got involved into it.
I thought we should come.
That all parts of Galois group are really not trivial. Some parts which do not.
Well, it's hard to hard to summarize.
Please.
In this kind of conjecture, do you have a condition that you ever want to be finitely generated group as a finite field? So in particular, does that make sense of a local field?
Ah, yes, so for a local field is true.
It is true?
Yeah.
What is true?
This assertion here is true over QP instead of Q. And actually, to be okay, so may I comment a little? Actually, I got some years ago very excited when I studied it, because I thought this is an approach to prove the local Langlands in this way, because actually the more is true. What one hopes is, I said here, okay, so Vx was this, what was here. But I'm very convinced that actually if you take Pn over Qp, and the Vx should be finally should be the complement of all possible QP lines. That means finally what you hyperplanes. Finally what you get is the Dirichlet upper half plane. I'm convinced that actually the theorem is true for that. And then at once you have actually something on which you have the Galois action on a natural object, from where then you can start doing something.
So this is a theorem of yours for QP?
Yes. But as I said, there are so many facts which one can prove, or maybe I can prove, but for me it's not clear at the moment what is interesting. I found that this is maybe something which is interesting, and then it's a kind of machinery after you understood this then.
But if you do what you are saying, you get into the combinatorics of the building.
Yes, you're right. Yeah, and exactly that's the point. So just got now an email from these guys doing hyperplane arrangements. And I say, look, we think that we got something arithmetical here. Maybe. Yeah, but you're right. So that's exactly that.
Very good.